I'm rather surprised that it happened in my lifetime. I certainly had no idea that it would happen in my lifetime at the beginning, more than 40 years ago, because at the beginning people had no idea about where to look for it. I'm surprised it's arrived as quickly as this. I spent the last week in Sicily at a summer school, and I went there convinced that the data analysis wouldn't have gone far enough for that. So it's really amazing for me to find out that it's really enough, shall we say, enough for a discovery claim. This verification of the existence of what appears to be a Higgs boson is just the beginning of, first of all, of a detailed exploration of what properties this thing actually has. It might be more interesting than appears just from a simple discovery. There are lots of things still to be measured, and that is going to be the beginning of a way into physics beyond the standard model, and that will be really the very interesting part. It's very exciting to be here at the moment, and I'm going to be looking forward to hearing more about it. The story begins with the work of Nambu and Goldstone in 1960. And this was a proposal that, by analogy with what happens in superconductors, that perhaps in particle physics, broken symmetries might be the result of an asymmetric vacuum state, in other words, the state where there are no particles, and nothing to do with explicit symmetry-breaking terms in the equations which we write down for the theory. So it was an idea which was imported from condensed matter physics. And the problem with the theories as written by Nambu, these were model theories, and by Goldstone, there was a prediction of some massless, spinless particles called Goldstone bosons. And this was not acceptable in terms of what was known, because they would very, very readily have been observed, and also they would upset our understanding of how stars radiate energy. So the problem that I got involved in 1964 was about how this theorem, which apparently had been proved as a rigorous mathematical theorem, could be evaded. And the first thing that I arrived at was the insight that the kind of axioms which had been used in proving the theorem didn't apply in quantum electrodynamics, which was at that time the only successful quantum field theory. So the clue there was that the field is the Maxwell's electrodynamics, and that has a property called gauge invariance, and that essentially is what prevents you from proving the theorem. So, having realized that, I asked myself, well, what would happen if we combined the Maxwell type of field theory with some of these models which involved spontaneous symmetry breaking? So I simply put together a model theory, a very simple one proposed by Goldstone in 1960, and I married it to Maxwell electrodynamics. And at that point, I saw in the equations of the theory that what happened was that what would otherwise have been the photon became a particle of spin 1 with mass. And the way it happened was that a photon has essentially two spin states, two polarization states, but a massive spin 1 particle needs three. The missing state is acquired from what were previously Goldstone bosons, so it all becomes an acceptable kind of physical description. So then I wrote a short paper about that, and I sent it off to Physics Letters, whose editor was at CERN, and they rejected it. And at that point, I thought maybe the paper was too short, and I hadn't said enough. The paper was about one side of A4, so I thought I'd better look at what were more physical consequences of this kind of theory. And I pointed out in a revised version that there would always, in this kind of theory, be some leftover spin 0 particles which did have mass, and these are what became known as Higgs bosons. But there was nothing particularly new about that. It was just that I drew attention to them. But the same sort of excitations occur also